Hello, my name is Adolfo Herrera, and this is the video presentation for Lab 4 for boundary layer theory for design of aerospace experiments. So this lab consisted, again, as I said, on boundary layer theory. This is our simulation which we use to compare data with the experimental values that we got in the lab and the theoretical sort of analytical solutions that we got from the lattice equations. Um, the simulation setup sort of looks like this. This is the 2D, this is a 2D sim. This is the 2D wind tunnel section that we use as the domain of the fluid, where there's the inlet, there's the outlet, and then we have our plate that we're testing in test section. Um, the geometry consists on the plate, the wind tunnel, the subtract, of course, which was batched for the 2D sim, and a volume refinement block, just more like an area refinement block. This is a 2D sim that was made here so that we don't waste any computation on areas that we do not really care about. Um, Also, now on that note, the prism layers on the walls of the wind tunnel are not that important, so no sort of mathematical estimations were made for these. For the prism layers on the flat plate, the Blasius equations were used to sort of estimate where the boundary layer thickness would be using the entire length of the plate and the free stream velocity. Um, and this is sort of how it looks like. It's not as perfect as it could be on the leading edge or on the trailing edge for that matter, but it works for what we care about. Simulation using the laminar flow model was run, and not evidently not much flow detachment was captured throughout the plate, and therefore another simulation was used using the K omega SST. Both ran simulation using the K omega SST model, um, coupled with the gamma model for transition flows. Just in case, because the Reynolds number for the entire plate does not exceed. We were not exceeding the laminar flow regime, so we're evidently not going to get any turbulent boundary layer in this sim. But just as a precautionary measure, I guess the simulation was ran using this physics model, where the solutions did not vary at all from, or not at all, but not as much from the laminar model sim. So this is sort of it for the sim setup. Here you can see the sort of results that we got, but these are not. I'm not going to present these in Star, or I made a PowerPoint presentation for them here, where I'll sort of it's more organized than it would be otherwise if I did in Star. So I'm going to just go over the different parts of the CFD assignment. So this is part 8, where I'll show the velocity contour. Not much to analyze here. As you can see, the boundary layer does not really decrease by that much. It's actually you can see better in the numbers. This is the vector field, which scores part of the assignment. Not a lot of data can be gathered from this. It's not numerical, and then this is the vector field and another arbitrary point on the plate. And moving on to part B, this is the plot comparison of the velocity profiles on the experimental data and the sim. They are quite different visually, but the sort of pattern, because the reason the simulation data looks like this is because it was gathered using, as you can see here, it was gathered using different probes on top of the plate. So if I go to derive parts, you can see that the there's a line probe on the 0.2 centimeter line, another one at the 8 centimeter. Um, point, and then another one 16 centimeters. Um, because the size of some cells are bigger than multiple of these probes, the vel some of the probes measure the same velocity. That's why they look like this. But essentially, it looks like a boundary layer um, thickness versus velocity plot should look like, where if you were to make these into a single point, it would just look like an exponential function. Um, on the leading edge, as you can see, sort of very close to the leading edge on the 0.2 centimeter point, it is not as smooth as on the other points. That's because you sort of, and you can see it on the, not only on the vector field, but on the velocity contour as well. You have some sort of uh, detachment where it's not really turbulent, but it's rather a laminar bubble that you're getting from this detachment because of the leading edge. Um, that's why it's sort of a little bit funky. But yeah, uh, the simulation values sort of show that the simulation is under predicting the boundary layer thickness with respect um, to the experimental data that we gathered. Um, Also, the velocity very close to the plate is this sort of makes sense even though it doesn't look like the experimental data that we gathered. Mostly because some of the probes that were used are very close to the plate where the velocity is close to zero because they're so into the boundary layer that you don't really have a lot of velocity there. Um, Now, moving on to the Blasius expression, this sort of looks more like the sim results, where you have this sort of exponential function here. And if you compare them, again, if you were to make these a single point, it lines up more with the Blasius expression than with the numerical data that we gathered in the lab. Now moving on to part D, which is essentially wall shear stress along the plate. This plot I got from STAR, not I didn't export the data to Excel, or I did, but then what I did with it was compare the two results. But essentially across the plate, this data is sort of not useless, but it's not representative or not really. It doesn't have the information that we care about because it contains the wall shear stress along the whole plate and not just the top part, which is the part that we're analyzing. That's why you have this sort of continuous line over here, and then this sort of waves that are not representative um, to the uh, to the top of the plate, which is what we're analyzing. So if we move on to the theoretical calculations, using these parameters, these three are gathered from assuming that the air temperature is at 15 degrees. Um, Using the analytical sort of expression from Glacius slides, the wall shear stresses were these for every one of the locations that we are interested in. Um, And if we plot them versus these same specific locations gathered from this plot here. So what I did was I went into Excel and I selected the same points across the plate on the top part. So like 0.2 and then 8 and then 16 and then uh, gather the wall stresses respectively for those points, you can see that the trend is sort of the same, but then the simulation results starts over predicting the uh, wall shear stress compared to the theoretical results. Um, if more points were gathered and then they were compared, what would probably happen is that the wall shear stress might follow the same trend of the theoretical one, but it's might be on top of it, meaning that it's still following the same trend, but it's over predicting the wall shear stress. And then moving on to part E, here we have the local skin friction coefficient, which looks exactly like the um, wall shear stress plot, since this is across the whole plate and including top and bottom parts of it. These are the theoretical results that we get from the same parameters that we use on the wall shear stress calculations for these Reynolds numbers. And then what I did was plot the skin friction coefficient versus the Reynolds number, and I did the same thing that I did for the wall shear stress plot, which was um, gathering the same points, 0.2, 8, and then 16 centimeters across the plate, and gathering the respective Reynolds numbers and uh, skin friction coefficient values. And it's sort of the same sort of trend can be seen in this plot from the wall shear stress one, where you can see that the simulation follows the same trend, but then in this case, it actually underpredicts through a specific section of it and then starts overpredicting them. And obviously, a better analysis could be made if more data was gathered and more points were used for the analytical calculation. And this is sort of it for this video. I know it was a little bit long, but I sort of wanted to go over the sim so that you knew that we did it work. So thank you.